Hey guys, this is Anchal from Vellore Institute of Technology. So today I'm here to explain you a very important topic of our physics syllabus that is known as fiber optics. So now, before getting into the discussion, let us first know from where the concept of fiber optics came into existence. Earlier, people used radio waves and microwaves to send data from one place to another. Then they attempted using light waves to transfer the data. The problem with the light waves was that they were open to the atmosphere, so they were very much affected by the hazardous atmospheric conditions like fog, rain, snow, etc. This created a lot of trouble. So then they thought of a medium, a guiding medium that they need to guide the light waves as well as to protect it from atmosphere. This gave the concept of optical fiber into existence. Let us start with the topic for our today's discussion, that is fiber optics. Before getting into the topic, first let us see what and all are the topics we are going to cover in this video. Firstly, we'll talk about the history and how the optical fiber came into existence. Then we'll see some basics of an optical fiber. Then we'll see how an optical fiber can be used as a waveguide along with the propagation of light in it. Then we'll see about total internal reflection along with the angle of acceptance and the acceptance cone. Then we'll talk about the advantages of using an optical fiber, and finally we'll go through its applications in our day-to-day life. So now let's start with the history of an optical fiber. The history of an optical fiber dates back to 1840s when the two renowned physicists Daniel Colodon and Jacques Babinet showed that light could be directed along jets of water for fountain displays. Then in 1854 came John Tyndall, who showed that light could travel through a curved stream of water, thereby proving that light signals could be bent. Then in 1880s, Alexander Graham Bell patented an optical telephone system called the photophone. And finally in 1950, the invention of fiberscope led to the evolution of an optical fiber, and since then we have been using optical fibers in our day-to-day life. So, fiber optics is actually a branch of physics where we study about the behavior of light wave inside a hair-thin fiber, where the hair-thin fiber stands for an optical fiber. So in fiber optics, basically we'll study about how the wave travels in the fiber, what all properties it displays while traveling, and etc. So this is how an optical fiber looks like in a real life. An optical fiber is basically composed of three components, that is the innermost core, the middle one cladding, and the outermost protective layer known as jacket or sheath. So, before moving on, let us first discuss what is the definition of an optical fiber. So, optical fiber is a thin flexible wire of glass core through which light signals can be sent with very little loss of strength. And what is fiber optics? The use of thin flexible fibers of glass or other transparent solids to transmit light signals chiefly for telecommunication or for internal inspection of the body is known as fiber optics. So, now talking about the layers of optical fibers. As I already mentioned, there are three layers in an optical fiber: the innermost core, the middle one cladding, and the outermost sheath. Here we have supposed the refractive index of core to be N1, that of cladding to be N. Now talking about the core. The thin glass center of the fiber where the light travels is known as the core. The cladding, the outer optical material surrounding the core, is known as cladding. And the sheath, the plastic coating that protects the fiber. The main work of optical fiber is that of the core and cladding only. The work of the outer layer or the protective layer is basically to protect the core and cladding from the environment. It is generally made up of polyvinyl chloride, or what we commonly call as PVC. So, the core and the cladding of an optical fiber are made from the same material, that is plastic or glass, but they differ in their refractive indices. If we suppose the refractive index of the core to be N1 and that of the cladding to be N2, then N1 will be greater than N2. Not very much, but slightly greater than N2. And now the role of the cladding. So cladding is necessary for light to propagate along the core of the fiber. The cladding reduces scattering loss that results from dielectric discontinuities at the core surface, and it adds up mechanical strength to the fiber. It also protects the core from absorbing surface contaminants with which it could come into contact. Now, coming to our next topic, that is total internal reflection. Getting into the topic of how light waves propagate in an optical fiber, let us first understand the concept of total internal reflection. So, in order to understand TIR, first consider an air-water interface with refractive index of water to be N1 and that of air to be N2. Now, as we know, N1 is greater than N2. As you can see in figure a light ray incident at an angle of θ1 gets out from the interface with an angle of θ2 from the normal, and it is bending away from the normal. Now, as we keep on increasing θ1, θ2 will gradually increase, and there will come a point which is shown as θc in figure B, that θ2 will become 90 degrees. And this angle is known as the critical angle, the angle at which the refracted ray comes out of the surface at an angle of 90 degrees. Now, as we increase the angle more than the critical angle, we can see the light is not coming out in spite, it's getting total internally reflected, and this is what we need for light to propagate in an optical fiber. Next, coming to the point of acceptance angle and acceptance cone. So what is acceptance angle? So acceptance angle is the maximum angle of a ray hitting the fiber core, which allows the incident ray to be guided by the core. As you can see in the diagram given, the ray is making an angle θA, which is known as the acceptance angle. Now, the greater the acceptance angle, the better the optical fiber. After this, coming to acceptance cone. So, in fiber optics, the cone within which optical power may be coupled into the bound modes of an optical fiber is known as the acceptance cone. As you rotate the acceptance angle in a 3-dimension, you'll eventually build up a cone, and that is known as the acceptance cone. So, in this diagram, as you can see, the green waves which are coming in the range of acceptance angle have been accepted by the optical fiber, and these waves are allowed to propagate further. Then comes the green dotted waves, which are exactly at the acceptance angle, so they are not allowed to propagate further. And after that, the waves which are very much greater than the acceptance angle, that are shown in the red color, they are not being guided by the optical fiber medium. So after this discussion, we come to 3 important points to remember. The first is, for TIR to occur, the angle of incidence should be greater than the critical angle. The second is, for maintaining the light inside the fiber, rays must propagate at critical propagation angle or less than that. And third, but not the least, To maintain light inside the fiber, we have to direct it from outside at acceptance angle or less than that. Now moving on to our second last topic, that is the advantages of using an optical fiber. So the first advantage is enormous potential bandwidth, that is the optical carrier range ranges from 10 to the power 13 to 10 to the power 16 hertz, and which is 500 megahertz for metallic cable systems. Then comes the second advantage, that is small size and weight. The optical fibers are very less in diameter, that is less than the diameter of human hair, and they are very easy to lay in cities, aircrafts, satellites, ships, etc. Now comes the third point, electrical isolation. Fabricated from glass, plastic, polymer, electrical insulators, etc. Therefore, no environmental hazard can affect it, no short circuits, and no possibilities of sparks. Fourth point is immunity to interference and crosstalk. Optical fibers form dielectric waveguides free from EMI and RFI. It is not susceptible to lightning strikes. No optical interference between the fibers. Crosstalk is negligible. Even many fibers are cabled together. Coming to the next point, the fifth point is signal security. There is high degree of signal security. Therefore, it is useful in military, banking, and other computer networks. The sixth point is low transmission loss. So it has a very low attenuation or transmission loss, that is 0.2 decibels per kilometer. Wide receptor spacing, that is long transmission distances without intermediate electronics. Then comes the next point, ruggedness and flexibility. It has a very high tensile strength. Fibers may be bent to small radii or twisted without damage. Then comes system reliability and maintenance. So it is reliable for 20 to 30 years. That's a big time. And the last point is potential low cost. So it is quite economic. Coming to the final topic of this video, that is the applications of optical fibers. So the optical fibers can be used in various fields in our day-to-day life, as they are very flexible. They are used in flexible digital cameras. The fibers are used in mechanical imaging, that is for inspection of mechanical welds in pipes and engines of rockets, space shuttles, etc. Fibers are also used in medical imaging such as endoscopy, laparoscopy, etc. Fibers can be used in undersea communications. These fibers can also be used in military applications like aircrafts, tanks, etc. Nuclear testing applications of optical fibers are also there. Fibers are used in LAN systems of offices, colleges, industrial plants, and many more places. Fibers are used in telecommunications such as voice telephones, videos, phones, messaging systems, etc. So here we come to an end of our video. Hope you enjoyed the video and understood the concepts well. Thank you for watching.